the oh, thanks, debunker. I forgot. um, Alec is from got his PhD from the group of Jim Crutchfield, who does a lot of work on the intersection between information theory and dynamical systems, thermodynamics, in particular chaotic systems, which are an important class of dynamical systems. I guess atmospheric systems tend to have some chaos, hydrologic systems not so much. Alec gave a very interesting presentation on the relationship between information theory and modeling and thermodynamics. So we asked him if he would give that talk here. And Alec, this group is, we meet every 3 weeks, basically a group interested broadly in information theory and its application to the geosciences. I think you know that. So, and now you're at Dublin, right? So maybe you could give us a little background, give people a little background before you start. That would be great. Thanks.
Sure. Thanks so much for the introduction, and also for the invitation to give a talk. For those of you that were at the workshop at Schneeferner House, there will be a lot that gets sort of that we'll retread together. This is a talk about thermodynamic overfitting and generalization, which is rooted in the idea of thermodynamic machine learning, which is something I'll explain later on. And it's really focused around the idea of sort of physical limits on predictive modeling and predictive complexity. So my background is in information theory, in basically the theoretical limits of predictive machine learning. And I'm currently working at Trinity College, exploring sort of predictive quantum models, predictive thermodynamics. But I also started this organization, our logo is down here, this institute called the Beyond Institute for Theoretical Science, where we are sort of pushing the physics of information towards the physics of intelligence, because we think that physics has very concrete things to say about predictive machine learning, which is the root of, say, transformers, which are the sort of the basis for so much of the AI revolution that we're in the midst of at this current moment. So with all that said, at a very broad level, this is one of the familiar slides for those of us at Schneeferner House. We have this Venn diagram to sort of bring different ideas to the physics of intelligence, ideas of machine learning, ideas of computational mechanics, ideas of thermodynamics, where information itself has physical consequences. And each of these different fields has their own specialty. Like thermodynamics is focused on measures of energy harvesting and useful energy production, which we refer to as work. Machine learning has a lot of different techniques for estimating models. Computational mechanics has a very firm framework for establishing ideas of complexity. And then you have overlaps between all these different fields. Inference is, I would say, one of the primary overlaps between machine learning and computational mechanics. And in the physics of intelligence, we're really looking at this three-way overlap in this Venn diagram. Now, what I'm going to focus on in this talk, it's largely going to be, we're going to use a lot of Venn diagrams. Here, there's sort of this hazy idea behind this Venn diagram, but there are actually some very formal informational concepts that come from this sort of analysis. So perhaps the first real artificial intelligence, one of the first conceptualized artificial intelligences was Maxwell's daemon, over 150 years ago, where James Clerk Maxwell proposed that this intelligent and neat-fingered being could interact with this thermodynamic system, this collection of particles trapped in a box of gas that has a partition in the middle. And the demon, by observing the particles and frictionlessly opening and closing this door, could allow particles to transition from one side to the other when they're moving quickly, but not otherwise. And in doing so, it would create a temperature gradient, creating a hot side on A and a cold side on B. And something we know about temperature gradients is that they can be used to produce useful work. So in essence, what this demon is doing is it's taking sort of the disordered thermal motion of these particles and turning it into ordered, useful energy work. So it's harvesting energy from thermal fluctuations using its intelligence. It's turning disorder into order. And this appeared to be a paradox because for those of us that are familiar with the second law of thermodynamics, if you have an isolated system, which this is, its entropy should in general be increasing. So, or non-decreasing is the technical way of saying it. So creating order is sort of the opposite of what we typically expect in physical processes. So if we see this glass in the midst of shattering, we expect it to proceed not towards a coherent, ordered state of, you know, a single glass holding liquid, but we expect it to continue shattering and into many pieces and scattering all over the floor in a very uncertain configuration. This means the second law of thermodynamics means basically that there must be some cost to the demon's mind operating. There must be some relationship between the fundamental relationship between a computation that's happening inside the demon's mind and the energy required to implement that computation. And maybe this is intuitive, like your cell phone requires a battery, your computer requires a battery, your mind requires your metabolism to run in order for you to think. Your cells, as they manipulate your DNA, they require ATP to function. So there are fundamental physical reasons that this is the case, and that are basically tied to the second law of thermodynamics, that any computation requires some amount of energy to implement. And you can see this pretty concretely. I'm going to show you one of my favorite simulations for illustrating this idea. So this is a simulation that of sort of an information storing system. Say the demon's mind is composed of an energy landscape given by this blue curve, and these particles represent possible configurations in this state space. Specifically, each one of them is an element of it's a possible realization, and all the collection is an ensemble. Now, the way that we sort of evolve the distribution of possible configurations is by energetic control. So we can do that by grabbing the center piece here and making it so that the particles can transition between the two sides. Now, notice that in doing that, we've raised the energy of the particles on average. And this red bar tracks how much energy we've put into the system. This is work that we've invested. And then we can tilt to get all the particles to one side. And then we can reset the system and to its original energy landscape. The purpose of that is so that, the only thing that changes is the configuration of particles. Oh, look at that. We've performed a nearly perfect erasure. This one particle has somehow escaped. And in doing so, we've invested some net amount of work that's over 2 kT. And this is in agreement with Landauer's principle. Basically, Landauer's principle would say that the minimum is somewhere around here. It's kT log 2. Energy is required to implement this erasure. So I'll put this link in the chat so that if you want to, or is there a chat here? Maybe not. Yeah, here we go. I'll put this link in the chat. If you want to play around with this, just grab the center thing to control. Control the particles. So this is sort of a concrete demonstration that, energy is required to transfer information.
Alec, can I ask a quick question?
Yeah.
Is it the case that that transformation could never happen without the energy input? Like, could it spontaneously happen given some amount of finite time?
Well, I guess it depends on what you mean by that process. So if you're talking about that collection of particles, which is about 200 particles, I think, spontaneously self-organizing to one side, that happens sometimes just through thermal fluctuations. You see in thermodynamics that you can have negative entropy fluctuations. However, when you consider the full ensemble, the distribution itself can't reduce without a corresponding amount of heat. So the second law of thermodynamics, entropy being non-negative, is a property of average entropy production, not entropy production for every possible realization. Does that make sense?
Yeah, actually. Great. Thank you.
Yeah. So, that brings us nicely to sort of the objects that we're considering, which are probability densities. So that ensemble of particles was meant to sort of give an intuitive representation of a probability distribution over some variable X. So here we use random variables to characterize a distribution, and their realizations are small variables. And the way this allows us to talk about entropy. So the entropy, or the Shannon entropy of a variable here, is minus of a random variable X is minus P log P, expressed in this way. So we consider the entropy of random variable X, the entropy of random variable Y, and we can consider the random variable of them together, the entropy of both together. So this is where we start seeing Venn diagrams. And this is, I don't know, to me kind of fun, because when we start to make these Venn diagrams, we can start identifying informational quantities. For instance, we can consider the conditional mutual information. So this is the uncertainty in X given Y, which is the joint, minus the entropy in Y. So that's just this wedge here. Can you see my cursor? I just want to make sure that, okay.
Yes.
Yep.
Great. So this wedge here, I think, is somewhat intuitively the uncertainty in X, given that you know what Y is. In addition, you can calculate the mutual information, which is basically the area in this wedge here. And you can do this with more variables. You can add another variable, Z, and we have this three-way information diagram where we have the conditional mutual information here between X and Y given Z, or the tripartite mutual information here between X, Y, and Z. And you can really get any of these information relations from the information diagram. You can see that, oh, the mutual information between X and Z is equal to the tripartite mutual information plus the conditional mutual information. You can just add up these areas. One interesting feature is that once you get to three variables, some information atoms, that's what these wedges are not necessarily positive. The tripartite mutual information can actually be negative. Not that we have to get into that, but it's sort of a fascinating feature of higher information atoms, or higher dimension information atoms. So why would we do that? Yeah.
Alec, Is that true even if you're dealing with discrete variables?
Yes, even with discrete variables, you can have a negative tripartite mutual information. It's sort of like related to synergy. So if two variables together determine a third, but individually they don't, you will see negative tripartite mutual information. So why are we doing this? Well, because we want to think about information as a fuel. So I presented this picture of Maxwell's demon where it was just spontaneously transforming heat into work, and that was impossible because of the second law of thermodynamics, because the demon would have to erase its memory to reset the process. But what if instead of erasing, it resets or it writes the information that it records to a hard drive? And in this way, you have this new information resource, an information reservoir, in addition to your thermal reservoir and your work reservoir. So basically, there's some energy content here, as well as some information content. You're taking the information content, putting in the information reservoir, and you're taking the energy content and putting in the work reservoir. And the second law applies to this system as well. You have the entropy of the thermal reservoir plus the entropy of the hard drive. That has to be greater than or equal to 0. And energy conservation basically dictates that the work production has to be upper bounded by the change in entropy of your hard drive. So this is basically a puts thermodynamic limits on the operation of things like a stochastic Turing machine, where you have a read-write head interacting with a sequence of bits. So it's like a thermodynamically constrained form of general computing. Now, if you take this, or if you take this stochastic Turing machine idea very literally, and you think about its essential elements, we might consider, say, we have some read-write head with some memory X that's interacting with a thermal reservoir at some temperature T, and a work reservoir as an energy resource. And it's interacting as well with an information reservoir, moving along it unidirectionally, transforming an input string into an output string. Then we can think about this as sort of a channel where, if we have our set of inputs here for a single time step and outputs here, and we transform the memory of so these are random variables. We have the output past, the input future, the current input, and the memory of the agent or the daemon. And you do some transformation that leaves the output past and the input future undisturbed. That's this portion and this portion, and transforms the new input to an output and updates the state of the memory. And so there's this general sort of object called an information transducer that logically captures this operation, where you have symbol labeled transitions between hidden states, and there's direct mapping between this and the joint Markov channel that you use to update the memory and the output of the system. And this is a very, very general form of stochastic computing. And as I mentioned earlier, there are energetic constraints here and they apply locally. So this computing subregion here has a minimum amount of heat that it requires in order to perform this operation. It has to at least dump KT, which is the thermal energy scale of the environment, times the change in entropy of this local region here, in order to ensure that it doesn't violate the second law of thermodynamics. And we can integrate over these operations more generally to sort of derive some interesting relations for how these machines operate. So if you integrate the operation over multiple time steps from 0 to t, then you have this sort of integrated transformation over the input past and the memory, the initial memory state, that you then map to the output past and your current memory state, leaving the future, the input future, untouched. And again, Landauer's bound applies locally, but the total entropy production includes the change in entropy of the whole system. So we have basically this bound on the heat, which comes from this local set of variables, but then this change in entropy of global variables. And that difference is basically comes down to a change in mutual informations, which we call the modularity dissipation. So any information between this locally computing subregion and this region, untransformed region, the output future, any mutual information that's lost through this transformation corresponds to irreversibility. It corresponds to entropy production that cannot be retrieved further down the line. So how do we understand what this constraint means? Well, here we go back to our information diagrams, where this is sort of the most general form of a 5-variable information diagram. You have input past, input future, output past, the current state of the agent's memory, the past state of the agent's memory, and the constraint, say that this has to be efficient, translates into some subset of these information variables being 0. But this is really, really difficult to do analytically. So let's simplify. So the way that we do this is we recognize that information engines transform patterns into work and randomly uncorrelated exhaust. So that means 2 things. First of all, it means that the dependence on the output future is actually 0. We also know that the initial memory state must be uncorrelated with the input sequence, because otherwise it has oracular information. And so therefore the modularity dissipation, the entropy that gets produced through this transformation, can now be evaluated in terms of this much simpler information diagram, where we just have 3 variables. We have the input past, the input future, and the state of the memory. Now, implementability, which basically means that the memory has to be a function of the past, basically insists that the overlap of the memory with the future outside of the past, and that's this wedge here, has to be 0. On top of that, efficiency, meaning that the modularity dissipation, efficiency, meaning that the modularity dissipation has to be 0, requires that these 2 informations are the same. The information shared between past and future, and the information shared between the memory and the future. And so that basically means that this atom here is 0. If we also insist on sort of a minimal memory, not just efficient, but not having any redundancy, we wind up with the following picture, where the memory of the agent is basically a causal state of the past, meaning it's a function of the past that captures all relevant information in the future. So this basically means that thermodynamics, designing an agent to harvest maximal work or to efficiently transform a thermodynamic information reservoir into useful work, allows us to derive principles of predictive modeling from physics. So the epsilon machine, which is a concept that comes from computational mechanics, comes directly by insisting that we minimize entropy production for a system that harvests energy from a pattern. So the statistical complexity here is basically the size or the entropy of the function of the minimum entropy of a function of the past that captures all relevant information about the past to the future. And epsilon machines, which are a highly interpretable prediction machine, these functions of the past are causal states. So we have A, B, and C, say, that capture the causal states for some process. They also are described by start state and symbol labeled transitions between the states. So if you're in state C and you see a 0, you know you'll be in A. If you're in A and you see a 1, you know you'll be in B. This is called the topology of the process. So if we have this function that maps, your current causal state and your next output to your next causal state, that sort of defines the logical architecture or the topology of your process. In addition, you have transition probabilities, which tell you the possibility or the probability of making any given transition from a particular causal state. So here, the theta of S given Y is the probability of outputting Y given causal state S. The reason I label it theta is because these are quite literally model parameters for predictive models. And the total set of model parameters here is the set of causal states, the set of outputs, the start state, the set of edge weights, and the topology. And from this, you can directly evaluate the word probability of a sequence of length L, Y0 to L, given some model theta, by basically just using a simple way of taking the product of a product of edge weights or edge probabilities. So the big picture here is that thermodynamics implies computational mechanics. If we insist on minimum entropy production, it requires that we predictively model our inputs for some sort of stochastic transformation of a pattern. This implies things like the principle of requisite complexity. The memory of the engine must at least exceed or must be at least equal to the statistical complexity of the underlying process. On top of that, the topology of the transitions among memory states is directly determined by the epsilon machine. So if we have some input process that's described by the following epsilon machine, if we have memory state transitions that are memoryless, we're going to necessarily dissipate entropy. But if we design the transitions of the system in the right way, of the memory in the right way that reflects these causal states, then we have zero dissipation. So basically, the memory updates according to the causal update relation or the topology. And so we have this tripartite equivalence between the estimated input model, its estimated epsilon machine, and the efficient agent that harvests energy from its process. So from one, you can determine each of the others. And this gives us a very concrete way of sort of interpreting thermodynamic data. So if we were to, say, have a collection of different models that we program into the efficient thermodynamic agents, say we have these different models here, different with different biases, different hidden states, and then we have some hard drive, and we don't know what's on the hard drive, but we're going to take some sample from it, some sequence of zeros and ones, and give each of these engines a copy, and then see how much work does it harvest. And then choose the agent that produces the most work as the maximum work agent. In essence, we're also choosing the underlying model as the maximum work model. And as it turns out, doing that will correspond exactly to a type of very familiar machine learning, because you can show that the work that's produced in this process, if the underlying engine has if the underlying model of the engine is theta, the work that's produced is kt times the log likelihood of that model theta given the data. This is basically the single shot version of Landauer's bound. If you were to average this out, this would give you Landauer's bound, but this is just so if you take the log the average over the probability of all realizations, it would give you the entropy. But here we can see that just for a single realization, we have this work production, plus the benefit here of randomizing L symbols. And so, this is the higher the log likelihood, the closer this is to zero, and the closer you are to basically obtaining a fully the closer you are to fully harvesting this amount of work.
Alec,
But yeah.
Sorry, that was a lot to take in.
Yeah.
Just pause a moment. I know Jonathan has a question, then I have a question, and I'm going to ask you to, if you don't mind, go back one slide and repeat this part.
Sure, happy to.
Thanks.
Yeah,
Jonathan.
here. Oh, sorry, I can't hear.
My question is actually about this part and the uncorrelated exhaust. Is the uncorrelated exhaust between the, I guess or can you explain that slide in terms of uncorrelated exhaust? Do each of those models have the same uncorrelated exhaust, or are they correlated with each other?
Right. So each of these models receives sort of the same input data, y0 to L. But because they're stochastically transforming the data to an IID uncorrelated output, the particular realizations of that exhaust will likely be different. But if you were to consider doing this process many times, the distribution of the exhaust would be the same. Does that make sense?
Yeah, that does. And then would there be anything identifiable about the maximum work production on exhaust?
The exhaust would be indistinguishable between all the different models.
Okay.
Unless you were performing something other than maximum work production. So there are other computational tasks that one might decide to perform. I'm just focusing purely on the task of harvesting energy from information. But I think other types of processes are very interesting. Like, for instance, reverse this process. Let's take random information and create a pattern out of it. What's the best way of doing that? As it turns out, rather than being predictive of the pattern, it's best to be retrodictive of the pattern. That's the most efficient way of creating information, which I think is a kind of fun and interesting symmetry.
Thanks.
So Alec, you said that you're going to pick the model that maximizes work done. Is that, I guess, useful work done?
Yes.
Which means there's the least amount of entropic loss, waste. I'm not sure. I'm trying to grasp the difference between these models.
Yeah.
They're all generating
Right.
identical streams of random numbers as outputs.
Right.
What's the difference between them? Yeah.
There's a subtlety there, definitely. So this comes back to the idea that entropy, while on average is non-negative, for realization, it can be negative. So if one sees this output string as a particular realization then the entropy production will sometimes be negative for some of these agents because they think that they are able to predict it better than is actually theoretically possible. And this is actually where we will run into ideas of overfitting. So entropy production and work production are very closely tied to each other. One way of quantifying work production or entropy production is to take minus the work production and add it to the free energy, the change in free energy. So the more that work that you produce, the less entropy that you dissipate, which is the basic relationship. Because these are all changing the free energy of this string in the same way, because the free energy itself is just a state function of the difference between the input string and the output string. Does that answer your question, Ocean?
Kind of. I'm getting a little bit more confused, but let's leave it for now. Let's leave it for now and come back to it, because what I'm interested in is, in order to do work, you have to do a certain number of operations, fundamental operations. And I sort of think of the number of operations you have to do as something related to the description length or the complexity, of the system. But I don't interrupt your stream right now. We can come back to it.
No, these are good questions and good for adding context. I think hopefully they're adding sort of. I think they're a little bit anticipating where I'm going to go. Also,
I was thinking, yeah. Okay.
But in terms of like description length, complexity, my way of describing complexity here is basically the topological complexity. So the number of memory states that the daemon requires. And so in each of these cases, really the number of operations is in essence just the length of the string, because it's making that many transformations, but the amount of memory that's required to basically keep track of the correlations is a reflection, or is sort of the way of quantifying the complexity in this case. Timothy?
I was going to wait, but you went there. So I'm trying to map this back to terms that I understand. So which of these terms is analogous or equivalent to minimal description length? Is it the H of S, the statistical complexity of the model, or is it HX, or is it something else?
I don't know if either is technically equivalent. I've wanted to go deeper into minimum description length and where it might play a role here, but I would say H of X is closer in conceptually to the minimum description length. It's kind of the amount of description you need to describe or characterize the model to a degree. But actually, when we go into regularizers, I'll give something that's a little bit different as sort of the I think something that's functionally similar to minimum description length in the way that it influences the way that you modify your model. But I like where the questions are going. I think maybe we'll go into sort of the numerical results, and hopefully more will be revealed in that case.
There's one more question in the chat from Dan. He says, do transition probabilities count in the complexity of topology?
Yes. In the measure or the regularization that I will wind up describing, they do come up. So there are a number of different measures of complexity. One of them is just the topological complexity, for which the transition probabilities don't count. But I think naturally one would also want to describe the transition probabilities. Good questions, everyone. Thanks. Okay, so there we go. All right, just to be fully explicit here about the parallel between machine learning and information thermodynamics, we have our data and we have our physical system, which encodes some data. And then we have a model of our data that gives us the probability of realizing this string of data. And then on the right-hand side in information thermodynamics, we have a daemon, an agent, a controller, and that thing has a model, contains a model in the way that it controls the data. And then on the left-hand side in machine learning, we have a performance measure like log likelihood that tells us how effective is our model at describing the data. And then on the right-hand side, the most natural performance measure for an information engine or a controller is work production, because that's useful energy that you've extracted.
Can you just clarify, Alex, when you say the model of the data, you mean the model that predicts the next value in that sequence?
In this case, yes. Yeah.
Okay.
It's basically density estimation.
Okay.
Yeah. And in this case, that work production is linearly related to the log likelihood. And so therefore, these are really equivalent frameworks to some degree. Well, okay, they're equivalent with the caveat that we are using epsilon machine models or predictive models to model our data. So what actually happens if we maximize our data? Well, this is where it gets kind of interesting. So here's our picture. We have an ensemble of agents, each characterized by a theta or by a model. We have our training data, and we do our thermodynamic machine learning, and we find our maximum work model. So let's say we constrain our memory size. This is kind of like a measure of complexity. And then we consider, okay, what's the maximum work amongst all models of that size? And what's the corresponding model that produced that amount of work? Just to be clear, when I'm examining this, the model that produces the data is this 5-state epsilon machine. This is something we label with theta prime. And because of the structure of this model, there's sort of an asymptotic limit on how much work can be extracted, which is given by KT times the difference in that between log 2 and the entropy rate of this model. And we also know that because this model has 5 states, requisite complexity tells us that we need at least 5 states to optimally harvest energy from it. So let's start with 1-state models. That means that all the different models that we consider are basically biased coins of various forms. So we have a hidden state A that transitions to A on a 0 with probability B and transitions to itself on a 1 with probability 1 minus B. And we can, from this, pretty easily evaluate the work production for any particular input sequence. And then we can train on words of length 100. And specifically, we train on words of all intermediate lengths, subwords of all intermediate lengths, starting from 0 to, and we see, the work production of this model proceeds as follows as you extend the length of the training word. So here's work equals 0. Here's a theoretical limit on the work that could be extracted from this process. Ooh, this is, sorry, Ocean, this is where we were talking about entropy production earlier. So really in this regime above, this corresponds to negative entropy fluctuations above this theoretical limit. Below this limit, this is where entropy is positive. Entropy production is positive. So this is, as we see, starts out high and goes to sort of a steady state here. If we give ourselves more memory, if we look at 2-state models and we find the maximum work model for all these training lengths, we start off high and then asymptote sort of like a lower value. And we see that sort of the negative entropy production regime exists for a little bit longer. And then if we give ourselves 3 states, we see that we asymptote to an even higher value in the negative entropy producing region, lasts for even longer. And in this comparison of larger and larger memories, we see that more memory always gives you a benefit in training. But how well did this engine actually learn the pattern? Well, for this, we need to do the next step. We need to do testing. So we take some test data and we feed it into the maximum work agent and consider how much work it produces on average.
Sorry, Alec.
Yep.
Just to clarify, the data came from a 5-state system.
Yeah, that's
Okay.
right. Yes, that's right. So this is all coming from theta prime. So we can evaluate this exactly. We have, basically we average over all realizations of the true underlying model, the work that got from our, so we have theta prime as our true underlying model, and we have our estimated model theta. And we can exactly calculate actually what the work rate is as L goes to infinity here. And for this exact expression, go to our recent preprint here. And what this basically tells us is that if we have some driving process theta prime and some estimated process theta, this tells us the rate that information is turned into useful energy. And here on the right side, we have sort of the testing work rate to compare to the training work rate. And we see that initially, this negative entropy production regime corresponds to what we call thermodynamic overfitting, where we actually have divergently negative entropy production because the learned agent is too certain of the transition probabilities. So here is sort of the this distance between the maximal work production rate and the work production rate of the engine is basically the rate at which this engine produces entropy, this distance here. Now, as we increase the amount of available memory, so this is the 2-state training, we see that the regime of overfitting extends. Just as the region of negative entropy production fluctuations extends. But we do see that as we increase the training word length, we harvest more energy. And then in the 3-state case, we see this trend continue even further, where we have very effective learning by the end. So this picture, altogether is as follows, where, you have this, region of the engine performing as a dud. This is the region where it's producing positive work and being useful. This is the region where on average it's producing negative entropy production. Fortunately, we don't see that happens anywhere. So therefore the second law is indeed satisfied by these engines. While, for particular realizations, we see that we have negative entropy fluctuations. So we see that there's a benefit of memory or complexity that can be seen in training, but that benefit only occurs in testing for large training sets. So we identify thermodynamic overfitting as high work production in training and high dissipation in testing. So what do we do to address this? Well, this is where we get into the idea of thermodynamic regularizers. So what should we do to our expression for work production to make sure that we don't wind up in these regimes of negative entropy production in training and high dissipation in testing? Well, one thing we might do is we could insist that the engine must autocorrect to the predictive state, and this incurs a cost to having unnecessarily distinct future predictions. So that means that rather than just allowing ourselves a unique start state, we have some distribution over our start states, and we evaluate the work production from each one. In addition, and this is where we come to different ideas of complexity, the edge weights must be initialized to their equilibrium energy, and that corresponds to dissipated work. So if you were to prepare, if you have some edge weight, that corresponds to causal state S and output Y, the energy of that state minus the free energy, which is going to be equal to the dissipation, is just equal to minus log of the probability of that edge weight. And if we have this complexity of the model that is basically the sum of these dissipations with some parameter alpha here just plugged in to allow us to tune that complexity measure, we can add that as an additional cost here to our training work rate. And this means that when we solve for the maximum work edge weights, rather than just doing frequentist statistics, we have this sort of modified expression. So this is sort of, what comes from maximum likelihood estimation. This is this modification to MLE that you get from implementing these two thermodynamically motivated regularizers. I'm not sure if this complexity measure is closely related to minimum description length. I would be very curious to discuss that possibility. With that said, we can go through these different cases and consider sort of the average behavior where we plot, an ensemble of training realizations for both the training work rate and the testing work rate, where these blue lines represent sort of the theoretical limit on how much work can be harvested. The circles are centered around the average for each strategy, and their widths correspond to the variance of the distribution of points. So the first case is what I'm just calling MLE, where you allow yourself a unique start state and the alpha is 0. So there's no cost to initializing your model. And what we see is that it performs very well in training, but there are a ton of realizations that have divergently negative testing work rates. So it's very bad on average in harvesting energy. The second technique that I'm calling Bayes allows you to start in a particular start state, but it has an alpha value of 1 because this corresponds to, when you look at the way that the edge weights update, this corresponds to Laplace's rule of succession, or basically the edge weights update according to Bayesian inference on a Dirichlet distribution. And that gives us sort of this red circle here. So we see a decrease in the training work rate, but an increase in the testing work rate. Similarly, we see an improvement when we do just autocorrection, so there's no cost to the edge weights, but we start uniformly over the all causal states. And this also, we see an improvement in the testing work rate and a slight decrease in the testing work rate. But I would say the best case is where we combine both uniform, the autocorrection and the Bayesian updates. This is what we call the combined method. This is the blue circle. And it's really performing the best in both cases. Or sorry, it's performing the best in testing and the worst in training, while the MLE performs best in training and worst in testing. And we can see this in much greater detail if we want, though, there's a lot going on in these graphs. If we look at different model complexities, n equals 1, 2, and 3, MLE, we see for different training lengths is, especially for a lot of memory, is very, very bad, even up to a training length of 128. We see that there's such high variance in the testing work rate, and that it's the average is well below 0 work production. With all the other cases, we see that we do much better. The Bayesian case is not that good, but we see that we have throughout the training lengths, pretty reliable behavior from the combined method, at least according to my view. I don't know if it's optimal, but it seems like a pretty compelling case for this sort of thermodynamically inspired regularization. So with that said, thanks for listening to my talk. I just, I think there are a few key takeaways, which are that maximizing work production seems to lead to learning complex models of patterns. But overfitting to small data leads to divergent dissipation, which is more common for more complex information engines. And so we see this picture that, say the true complexity of an input, say, is here. If you have a too complex agent, there's sort of a thermodynamic impetus to reduce your complexity. And if you have an under complex agent, there's a impetus to be more complex. So there's sort of this complexity matching that seems to happen. And we also see that thermodynamic regularizers lead to learning that more effectively generalizes. So with that, we see this broader picture that, not only does driving a system to harvest energy lead to prediction, but also there are thermodynamic principles for regularization, which means that resource optimization seems to lead to principles of predictive learning. So I'm very curious to continue in this line of exploration. If anybody has any further ideas for how these overlaps can be explored, I'd be curious to chat more. I'd just like to thank, my collaborators on this project. So, yeah.
Thanks, Alec. That's great. Before we go too far from your last comment, could you just go back and clarify the two kinds of regularization again, just so?
Yeah. Right. So one of them basically insists that rather than starting in a unique start state, this is autocorrection. This means that there's a work contribution from every initial or every memory state of the daemon. And this avoids the issue of, say, you have a very large memory, a memory that's, say, larger than the length of the string that you're trying to predict. If you have such a string, you can always find a deterministic way of producing that from a unique start state. But if you require that you consider the probability from every start state, then you're going to find that deterministically producing it, or basically encoding that data directly in your memory, is going to lead to divergent dissipation.
So to regularize, you would take into account all the possible states and run your model from all possible states, and then combine those into this likelihood function, which you then maximize. Okay.
Yeah. Right.
So you're basically integrating out the uncertainty in your initial state in some sense. Something like that.
Yeah, that's exactly it. I'm not sure. That must be a technique that's implemented somewhere in the literature. I'd be curious to know for machine learning. So, and then this
the alpha. Yep.
This cost here is basically, if there's, it basically incurs a cost to having low transition probabilities, or being overly certain of certain transition probabilities, if that makes sense.
So I'm trying to understand the equation on the bottom right there. You're multiplying your initial probability, the state probability, with alpha plus n. So if alpha is 0, so remind me again what n was.
Sorry. Oh, my bad. One sec. I realize I didn't fully explain this, the math behind this equation, but N is basically comes down to counting statistics. So if you look at a particular word with a particular topology and a particular start state, that will therefore tell you the number of times input Y visits causal state S. So you basically do some counting statistics, and then
So that sets, if you set alpha to 1, that sets the minimum number to be at least 1. Yeah.
Right. Yes. So if you set the minimum to 1, this gets you away of the problem of, okay, if you don't see any outcomes that combine output 0 with causal state A, that will lead you to inferring that 0 has 0 probability coming from A. But that's a very extreme assumption to make. In fact, if you make that assumption, and if you ever see an output A from, or 0 from A, that will correspond to infinite dissipation. It will break your machine.
Got it.
Yeah.
Thank you. Geshe.
Thanks for the talk. I like the idea of comparing the thermodynamic theory with the machine learning. Well, I actually have the same question over here. When you're talking about states, I mean, I'm thinking about in the neural network scenario, right? Do you refer to all the states, including the inputs, hidden states, and the outputs? It's kind of if you consider the model complexity, it has to be all of them, right? Trying to think of the comparison between the thermodynamic regularizer with the commonly used regularizer that usually account for the number of the states, hidden states used in the model.
Right. So I guess the most direct comparison I would make between like a neural net would be a recurrent neural net, because those react to and predict a time series. So I would say, yeah, the idea of a particular state or configuration in a recurrent neural net, since it's a bunch of different continuous values applied to, that are encoded in weight matrices between different nodes, it's hard for me to know what the natural idea of like different states are within that neural network.
We would need to think of a discrete set of states at each node, at each recurrent node.
Yeah.
Be able to understand that, I think. Yeah.
I think it's, my impression is that functionally, often these neural networks will naturally arrive at something like a discrete set of states, but I'm not fully, knowledgeable about this topic. But yeah, the regularizer is conceptually similar, I think, in that, it's using a function of the weights. Like in a recurrent neural network, you would have, a function of the weight matrix, right, to sort of add. Or for instance, in a reservoir computer, you would often have a function of the weights there. Seeing some comments.
Okay, thanks. I actually have another question. So I'm not quite really follow all the equations. I mean, that's too much for me. Just from a general understanding, does that mean that a model with a higher complexity would potentially generate high dissipation in the testing data set?
Yes, I would say that's.
Do you have a concise equation that is able to describe it? That would be cool.
No, I don't yet. I would really like to understand if there's some limit on that. I suppose one of the things I've been thinking about, though, is the Fisher information. as a way of accessing that. So that's a place to go, certainly.
Okay, thanks.
No, thanks for the question.
Joseph?
Yeah, could you go back to the implementability constraint?
Yes. That is a while back. Yeah. Implementability, right
Right.
here.
Okay.
So,
Ye-
yes.
Yeah, I might ask a question about that later, but it just reminds me of something else. I just had to remember what it was. For a different question while I look at that, do you have like, I mean, there's kind of different definitions of overfitting. Do you have some ideal model in your head when you're doing those plots? Like, given that the test set is as high as possible, do you want the training set kind of error to be exactly the same as the test set, or do you want it to be less? I mean, if you think about humans, like, uh, I would say their training set error would be less than the test set error, even though we can generalize pretty well. So,
Yeah.
like, how do you think about the ideal model in that case?
I guess my intuition says that, if we have a good method of inference, the training error will be closer to the testing error. But I don't have a formal understanding of why that should be. That to me is an open question, like what I should expect for the testing error. But my impression is often if you harvest more work than is theoretically possible, that generally corresponds in training. If you harvest more work than is theoretically possible on average in training, that will likely mean that you've it means that you've overestimated your certainty of your model, and therefore you're going to have some errors down the road. How big those errors will be in testing, I don't really know, but I'd be curious to see if there's some bounds we can put on it. Does that answer your question?
Yeah, it does. Thank you.
Okay.
Any other questions? Otherwise, I have the question I've been wanting to ask Alec for a long time. So, Dan, did you have one? Go ahead.
Yeah, so I put it in the chat, but while we were sitting on that one slide towards the end, where you're describing the difference between the four approaches, maybe it was like 5 or 6 slides from the end, and you were discussing the difference between you had N at the top and you had P of S at the bottom.
Is
so
this
the
one?
4 equations at the bottom of the screen. Sorry, I think it was like 90.
This
Yeah,
one.
there.
Yeah.
Yeah. So on the right-hand side, the difference between the top and bottom, that's my question here.
Yeah.
Does that represent the Dirichlet prior that you were mentioning? So is that like, is N like a constant pseudo count? So it's a uniform distribution across the state space, whereas the bottom is non-uniform based on the training data, basically like the observed counts in the training, or
Right. So if you choose alpha equals 1 here, then the weight that you get here is basically the Bayesian posterior, if you assume sort of a Dirichlet prior over the edge weights. So in the case where you only have 0 and 1, that means that your prior is uniform over the probabilities of outputting 1 being 0 to 1. And if you choose alpha equals to 1 in this case, that, yeah, basically just means that, you know, if given that you've seen this number of inputs, this is the corresponding Bayesian posterior. Does that make sense for that particular prior?
It's not totally clear, but yeah, it's moving me closer to it. I think I just need some time with it. But
Yeah.
thank you.
Absolutely. It's a little bit of a it's a little bit of a finicky. It's hard to describe. You can definitely go to this paper if you want more details on it, but I'm trying to think if there's like a simpler way of saying it. But basically, Laplace's rule of succession, you know, which is for a single variable, basically says that, well, think of it this way. You know, if alpha equals 1 and this is, forget this coefficient and just think about what's inside of this divided by what's inside of this. This is basically the total number of counts of S, and this is the total number of counts of S and Y together. If this is 1, and you see, you know, 5 zeros on the bottom, and or so 5 total counts and 1 count of 0, this, or 0 counts of 0, this will give you 1/6, right? 1/6 probability of 0, which will be sort of the Bayesian posterior that corresponds to assuming something uniform in your distribution over possible probabilities of 0. Sorry, I feel like I'm muddling my words here, but hopefully that makes things a little bit clearer.
Yeah, I'm gonna go into the paper because I'm curious about this. Yeah.
Okay. Yeah.
Thank you.
I feel like a blackboard would be helpful in this case.
That's
But
okay.
yes,
Yeah.
it's a good question.
Thanks.
All right.
Hey, if
Ocean?
you don't mind. Okay. Yeah.
Yes.
I think it's related to your talk, but it's slightly more general. Yeah. I'm an organism and I'm wandering around in my environment and I'm getting sensory information based on which, so X happens and I want to predict Y.
Yeah.
So I want to know what to expect. When I see X, I want to know what to expect, say in the next moment. Yeah.
Right. Yeah.
And I've got limited amount of memory and I've got limited amount of processing power by virtue of the fact that I'm some kind of physical organism. And I can start by just storing all the data that I get, but and using something like nearest neighbors, you know, to say, well, whenever X happens, what's the closest thing to what happened in the past? And I can use that to predict, right? That's no model, it's just storing all the data and searching it. But at some point, I'm going to have too much data. I can't store it all. So I'm going to have to store a compression of that data.
Yeah.
Okay, I'm going to call that a model. Okay. So I'm going to call that a model or some kind of information. Okay. Now, the conventional view of algorithmic information theory is that you want to store or have the shortest possible version of that model. That would be the description length version. Yeah. And that if I had to choose between two different representations, I would choose the shorter one because that's more efficient in terms of memory storage. Okay. But what I've been thinking about is the fact that what I actually probably really want to do is I want to store the model which requires the minimum amount of work done to get a prediction of sufficient accuracy that I can make the right decision so that I can survive, right? And so it's not necessarily the shortest description, but the one that requires me to do the least amount of work to get the outcome that I want. And so that's how I've been trying to relate description length and work done in some sense, because I could have a very short description, but it requires me to do a lot of operations to get the answer I want. Or I could have a longer description, but it's a smaller number of operations. And probably to survive, I'm going to try to minimize the amount of energy expenditure I need to do. Does that sort of see where my question is coming from? So I'm
Yeah.
going to look at the entropy rate on my test thing, and I'm going to try to keep that within some acceptable bounds. It doesn't have to be minimal. It just has to be good enough that the lion's not going to eat me. I'm going to
Yeah.
survive
Yeah.
long enough to propagate my genes or whatever. Yeah.
Right. Yeah. I mean, I think I see things in a similar way in a lot of ways. Though when you were talking about minimum description length as sort of the um, minimum amount of information one needs to store from the past in order to predict the future, to me, that's the statistical complexity through and
Yes.
through.
Yes.
Here's that function of the past you were talking about, right? Or right here. But I'd say sort of the idea of this cost, balancing the cost with the benefit, to me, is most similar to this complexity cost here, right? Where this thing, when alpha is equal to 1, really I interpret it as the cost of instantiating your model, right? Not just forming the memories, but actually forming the memory and then tuning the edge weights to be just right, such that you can make a prediction using your memory. And I would also say that my view maybe is subtly different than yours, also in the idea that I don't necessarily see it as like you're doing the bare minimum to survive so much as you're just given this constraint that you have to instantiate the model. You're trying to harvest as much energy as possible just because energy gives you competitive advantage. But I don't know, maybe that is the way. Maybe optimization isn't quite the way that life works. Maybe it is more just about like just enough to be beyond a certain threshold, which would maybe give more space for speciation and like diversification. I don't know.
So I'd agree you want to maximize energy available to you for whatever purpose, not just survival. I agree with
Yeah.
that. But I'm sort of looking at if I take the simplest possible machine learning model, which is I just store my data
Mm-hmm.
in a lookup table, then I have to do a tree search kind of thing, and there's some optimal tree
Yeah.
search strategies, and there's some amount of energy I have to expend in order to find the answer I want. Yeah.
Yeah.
Now, at
Yeah.
some point, I go, geez, this is too much energy because my data set's too huge, right?
Yeah.
So let me replace it with a linear regression. Okay.
Yeah.
My description length on a linear regression is very short compared to the data. Yes.
Mm-hmm.
I don't have to store X. I don't have to store Y. I just have to store Y and X and C in an addition term or whatever, right? But my error goes up. My entropy, like my predictive error goes up because it's probably going to be worse than if I'd stored all the data.
Yeah.
And so now I have a lot more energy, as you said, to do a lot of things. I have to do a whole lot less work, right? And so there's an evolutionary pressure on me to simplify, if
Yeah.
it makes sense. Yeah.
I
Yeah.
agree. I'd say this overfitting is evidence of sort of this evolutionary pressure to simplify. Um, and uh, and also just practically the fact that if you have a more complicated model, it seems as if you need to take more resources for your environment to create that model. So I'm sorry to say this because I'm really enjoying the conversation, but I do need to head off in 5 minutes. Maybe I can take a few more questions and then one or two and then head off.
We'll talk some other time. Thanks.
Yeah, thanks so much, Hoshin. I really appreciate it. Jonathan, sounded like you
I
had a
had some
question?
comments on that same conversation, but I think we should move on if somebody else has a question.
I don't see any other hands raised, so why don't you go ahead, Jonathan, and that'll be the last one. Yeah.
I guess it's not really a question. That's why I was hesitant. But in both the scenarios that you described, Ocean and Alec, there's also like this secondary model that you need to know if the agent or the organism needs to make that trade-off, and if there's a balancing point between that trade-off. So there's a model required even to know to make that trade-off.
Right. There's some background processing. There's a dictionary. I mean, Jim Crutchfield talks about when you transition to a tree-like structure to a different level of epsilon machine, right? Yeah. We haven't talked about that in any detail, but that's interesting.
Yeah.
I guess I'm wondering, is there just a hierarchy of models all the way down?
Well, maybe. Yeah, I think about that sometimes in terms of how one naturally explores these models, how you sort of organically increase your complexity or reduce your complexity to sort of adapt to the situation at hand. Like what would be, the way that I'm doing these optimizations is brute force at the moment. And the direction I'd like to go is towards sort of a more organic, thermodynamically inspired optimization method where new causal states spring into being through thermodynamic processes, as opposed to just saying, we'll say that we have 3, or we'll say that we have 2, or and where the topology of the transitions amongst those causal states is again organically and thermodynamically dynamical. So I don't know. I'm curious to go in this direction. I think it's very unknown to me. I don't have anything concrete to say. Just interested.
There is some work in Jim's early papers on epsilon machine where he talks about you go from just the data to a decision tree structure to the state space diagram thing. In some of his early work, he talks about that, and how in computer science you have different kinds of memory, like push memory, pop memory, and you have these more and more complex state space model structures.
Yeah. There's a hierarchy there. What classes of models can contain others, push down automata, things like that. Yeah.
But we should let you go. This has been very inspiring. Thank you.
Thank you so much. It's been a pleasure getting to see you again and share some of what I've been thinking about lately.
That's great. Hopefully we can get you back sometime and pursue some of these other threads at another time. Yeah.
I'd be delighted. Yes, please. I look forward to it.
Okay. Thank you.
All right. Thank you. Bye.
Bye, Alec.
We should probably just leave this, so it will save this recording and
Right.
Lisa will upload on YouTube like whenever she gets a chance.
You can stop the recording, I guess.
Okay, yeah.
You want me to do it? I can do it.
Mhm.
Stop recording.